everyone, hi, this is Sachin. Welcome to my channel Redirect AI. So today we are going to discuss some of the applied statistics techniques. This is recording from one of the live sessions that I had taken in one of the corporate trainings that I had undertaken. So in this session, you'll get to know more about basic statistics and descriptive statistics. Since it's a 2 hour long session, so I suggest that you divide this session into two parts and finish it in two attempts actually instead of one. That way you can retain more knowledge, and it will be in fact useful to you that how can you apply this basic statistics and descriptive statistics to day machine learning tasks. All right, I'll see you in the session then. In today's global business and economic environment, which are the main pillars of economy, anyone can access vast amounts of data. And when it gets to data, now we can access vast amount of statistical information. In statistics, data is mostly referred as statistical information uh, instead of the term data. The most successful managers, why I'm saying managers, because we all are working professionals and we don't want to get into research of statistics, but we want to get into the applied form of statistics. So the most successful managers and decision makers understand this information and know how to use it effectively. So there are certain ways people take decisions, either basis their experience, basis the facts, basis the analysis they get from the data. But when combined with statistics, it becomes a very powerful tool for strategic decisions and calculated, or you can say calculated decisions or calculated risks, everything. So today, I'll try to cover such uses of statistics, starting from basic statistics in business and economy. Starting from the definition, what is statistics? In layman term, it's just a simple art and science of collecting, analyzing, presenting, and interpreting the data. Now we have got the four terms here. Collecting. So first of all, we have the data sources. We collect the information. Then we analyze it. In analyzing, pre-processing also comes there. Then we present the data, whether it's in Excel, whether we have the BI tools, or whether we have a ML model. And finally, we make some conclusion from the data that we interpret it. Interpreting is basically for the end users mostly. Now, statistics is a in technical terms, it's a collection of mathematical techniques. Every data problem, every statistical information problem can be converted into mathematical problem, and then using the certain predefined mathematical techniques, we can solve those problems. So it is a collection of mathematical techniques which help in validation of strategic decisions and understand various business economies better with underlying insights from the data. So basically, it's a usage of some mathematical techniques to validate our hypothesis, maybe, or to take certain decisions and understand underlying data much better. For example, we have example in marketing. So let's take an example of retail store like Spencer or Walmart. Many companies, many marketing companies, many FMCG companies buy this point of sale data from the retail counters, and they process this information to gain more insights at that about how their products are being consumed by the consumers, and what products are bought together, what other analysis, what product has the longest shelf life, what product has the minimum shelf life, which product should be kept together, and then certain decisions are made on that. So it's all a collection of, now when I said what products are bought together, some of you must be thinking that, okay, it's a use case of machine learning. But at backend, it's a mathematical technique only, that a priori algorithm that we use for what products are bought together in machine learning. But at backend, it's a mathematical technique. And when we get into the realm of mathematics, statistics is bound to be there. The other is production. Now we have all seen a very this drink called Coca-Cola, right? So it's a automated facility that every bottle gets rolling on the conveyor belt, and the machine fills in the soda in it and then mixes the flavor and whatnot. Now, from time to time, how do they check whether in a 600 ml bottle, whether the amount of liquid that is going in is 600 ml only, right? So it's not the case every time, because sometimes it can be 599 ml, sometimes it can be 601 ml, and that would actually happen if you'll go buy 30 different bottles from 30 different stores. You will get that variation because it is bound to happen. That is the normal nature of machines and how things work. But how do we detect that thing? So that is what, using statistics it is done. Sometimes, if the bottle is getting filled by 1 ml less, it's loss for the consumer. It's profit for company, right? Because company is getting paid for whole 600 ml, and when it's 601 ml, then it's loss for the company. But somehow company manages to apply statistics on that, and uh, recalibrates the machine. Even if it's 599, if it's 601, the machine will be recalibrated basis some mathematical techniques, or also called as statistical tests. Then in economics, very common example is forecasting the price of gold, forecasting the price of crude oil, forecasting the price of, or we have the stock market all over the world and whatnot. So here we got the four crucial terms out of this definition, that we have some data that we collect, analyze, and present. On this data, we do some validation using some mathematical techniques, and we take some strategic decisions. In terms of statistics, data will further bifurcate into the types of data we have. The validation means using various statistical measures. Then we have the mathematical techniques or various statistical tests. So these are used interchangeably. These two terms go hand in hand. That using some mathematical techniques we validate some our hypothesis. Hypothesis in layman term is that our guess, or you can say our estimates or our guesstimates. Or these are also called as guesstimates, and we take a statistic decision, which is the finally the hypothesis system. Moving on. Now we come to the data, the very common fact everybody is aware of. So data are nothing but simply the facts and figures collected, analyzed, and summarized for presentation and interpretation. No hard and fast, no technicality in this one. All the data collected in a particular study are referred to as the data set for that study. So this is the statistical definition. We can ignore this one. No worries. Now, data has three main elements. One is three components, sorry. One is element, one is variable, one is observation. Now, variables are the part that are referred as columns in layman language. Elements are the entities on which data are collected. And observation are again the set of measurements or the values obtained for that particular thing. Let's learn by an example. Now, in this example, you see it's a data set for some mutual funds. Now here we are collecting data for mutual funds particularly. So mutual fund are the elements in this data set. What kind of information we are collecting is that we are collecting the fund type of mutual fund, the NAV, the 5-year return, the expense ratio, and the some rating agency rank Morningstar. So these would be called the variables or the columns. So in machine learning also we refer columns as variables. Sometimes these are called attributes as well. And these information that we have recorded for each particular combination of element and variable is called an observation. So far so good. Now we come to the type of data, which is the most crucial part, and I think most of the analysis that we do in any kind of field in data analytics, whether it's machine learning, BI, or simple data analysis, the type of data is very crucial part to understand. In type of data, we have two things. One is scale of measurement. So on what scale the data will be measured? Normally, data collection requires one of the following scales of measurement. So these are for generalized scale. One scale can be out of it as well, but to keep it on single axis, I have put this four categories. One is nominal, one is ordinal, one is interval, and one is ratio. Now, ratio is predefined. Ratio is self-explanatory. Interval may be self-explanatory. Now, what is this nominal and ordinal? And why the scale of measurement is important? The scale of measurement actually determines the amount of information. You know, just please follow me here. The scale of measurement determines the amount of information contained in the data and indicates the most appropriate data summarization and statistical analysis. So basically, the scale decides what kind of data analysis is going to be applied on this kind of data, right? So now to learn more about these four scales, and since I think you already have this machine learning training, so in machine learning training as well, if we have nominal data, the data pre-processing would be different. In the ordinal, data pre-processing would be different, and likewise for interval and ratio. So that is why scale of measurement determines what kind of, which is the most appropriate data summarization, pre-processing, or analytical technique which will be applied. Now, going to the nominal. The nominal is simply, it's simply a data for a variable consists of labels or names used to identify attribute of an element. Let's go back to this data. So here I would say that nominal data is basically to refer an element or to refer, certain observation or certain recorded information. From this example, I would say, that this the fund name here is the nominal information, because I can put this American here on the last row or maybe in mid of it. Nothing will change. The rows will be sorted accordingly, and there's no order, dependency, or there's no foundation of why this should be on top, why this should not be in middle, and likewise. Similarly, for font type, we have certain values which are again repeating, not an issue. Like IE stands for, I think, international equity. FI, I don't remember exactly. I think FI should be fixed income, and DE should be direct equity, and so on. So this kind of information has no order. Americans actually can go here. It will be recognized easily that it's a IE fund type. So this kind of information which does not follow an order and can be jumbled up according to our convenience is called a nominal data value. Now this nominal data value, here I can also assign numbers to it. For example, I can assign 1 to IE, or 2 to FE, 3 to DE, and this column will change likewise. Now this number is not a magnitude but a category. Yes, Ankit, you have a question.
Yeah, Sachin. So basically, what I know here, and correct me if I'm wrong. So nominal and ordinal are basically a type, or I would say category of a categorical data type, right? Like ordinal is something where you can do the ordering, and nominal is basically text which don't require any order. Is it a true
Right.
statement? So they say that?
Yeah, right, Ankit. Yeah.
Okay, so how is it helping in our scaling? So you just mentioned about deciding the scale part. So
Mhm.
how it is helping? Because normally on a scale, we usually see a kind of a classes or a continuous data or a kind of discrete data. So how
Mhm.
nominal data will help us in scaling?
In scaling, okay. So the nominal data, Ankit, would be referred as a plain categorical data. Since I haven't explained that part, but I would like to answer this question. So this is for Ankit only. Whatever terms I use, like categorical data or numerical data, we'll learn that later. So Ankit, for nominal data, right, it becomes a categorical data. So your choice of visualization would be different. You cannot take a line chart with the nominal data, but you would like to go with a bar chart or a pie chart maybe, right? But when I talk about the ordinal data, definitely the order of magnitude would be different. Now, the choice of visualization would be same, but kind of pre-processing would be different. Why? For nominal, suppose we have three orders, three categories, one, two, and three. Now, I can, I can make one as three, two as one, three as two, right? That won't make any difference. I can interchangeably use these terms because I'm not using number as a magnitude, I'm using number as a class only. But in case of, let's say, ordinal data, the rank, I cannot, just assign rank 4 to a mutual fund which is actually a rank 3, right? So that is how the magnitude of the observation. Now here it's 3 star. I can use 3 as well. I can use 4 instead of 4 star. So that is how, the scale of measurement will entirely change. Here we are considering one second attribute of this observation, which is the magnitude or the ordering. So that is how it changes.
Okay.
Does that answer your question?
Yeah.
Okay, thank you. All right. So moving forward, we just understood what is nominal data. Now comes the another category of data, which is called the ordinal data. Now, ordinal data is the nominal data only, but with one added attribute, the ordering. That is, the order will matter. I cannot, if American Century is on rank 3, I cannot put it on rank 5, right? Because that will entirely squash the nature of this data, and the data will get corrupted on, and the data will not be authenticate anymore. So wherever this kind of information, where it is nominal but ordering is very important, that becomes an ordinal data, as the name suggests. So the scale of measurement for a variable is called an ordinal scale if data exhibit the properties of nominal data and order or rank of data is meaningful. So we just learned that for nominal fund type, or maybe the name of the fund is nominal data, but for ordinal it is actually the rank. Now, one thing I would like to reiterate here, that I have referred this fund name as nominal data. Usually, it's a nominal data only, but the data under discussion is these 5 variables only. So, fund name is actually nominal data, but while doing the analysis, we won't be doing any kind of summarization or visualization on fund name. So rather, we'll take fund name as ID column for unique like a primary key purpose and data. Now, another scale of data measurement is interval. Now, interval, as the name suggests, that we have kind of interval and some values would be falling under that. Now, the scale of measurement for a variable is interval scale if the data have all the properties of ordinal data and interval between values is expressed in terms of a fixed unit of measurement. For example, now what is happening is we had the nominal data, we added the ordering in it, it becomes ordinal data. Now in that ordering, we categorize that ordinal data into some different categories. This becomes an interval data. For example, uh, we can say like score intervals for students, or maybe intervals for 5-year return. Now let's suppose, what I do is, according to the rank, I take out what is the 5-year average return for each of them, or maybe if I ignore the rank and I just simply refer to this 5-year average return, and I categorize this into some kind of intervals. For example, how many mutual funds lie in 0 to 20% 5-year average, then 20 to 40, 40 to 60, 60 to 80, and so on and so forth. So that would be the interval data, and this data set would change. Some kind of analysis has been applied, and the scale of measurement will also, the original information will remain intact, but the scale would change. Then comes the ratio data. So ratio is nothing but the division of two numerical values altogether. Now the scale of measurement for a variable is a ratio scale if data have all the properties of interval data and the ratio of two values is meaningful. Now, what is happening is, that from nominal we add the order, becomes ordinal. In ordinal, we add the some kind of one more category called intervals. it becomes interval. And in interval, we add the ratio of two value, we add the properties of all interval data and ratio as well, then it becomes the ratio. Uh, that so there's no more, definition for ratio. It's self-explanatory that, in case of mutual funds, like we have the expense ratio. So expense ratio is basically a financial term which suggests that expense, uh, what kind of expense from your investment goes to administrative purposes. So, for example, if I've invested 10,000 mutual fund, the actual investment won't be 10,000. It would be maybe 10 rupees less or maybe 20 rupees less. So that is where the expense ratio comes from. So lower the better. Lower the better. Okay. So we just learn about the type of data and with respect to data measurement. Now let's come to the data classification. So in data classification, I can say we always have only two type of data. One is quantitative, which can be quantified, or it is referred to as numerical as well in respect to data analysis. And one data is categorical. So as the name suggests, this quantitative data is the data which can be quantified. For example, uh, if I go here, the net asset value, it's a quantifiable of quantity, right? Similarly for 5 year average, similarly for 1 year, and similarly for this rank as well. Now this rank, it can be, taken in two ways. If we take it as 3 star, it becomes a categorical value, and if we take it as number three, it becomes a numerical value, whose magnitude is also relevant, right? So rank is also quantifiable. Sometimes we get confused whether ordinal goes into categorical or numerical. Now that depends upon the data representation. If it is in numerical form entirely, it becomes a quantitative quantity, else it becomes this categorical quantity. So to give one a very beautiful example of how this ordinal scale can change the way I applied a machine learning model in one of my projects. So what happened is, this is some customer feedback. We had to predict the final overall rating that the customer will provide. Okay. So I'm just not going into details. I'm just telling the final dependent variable was the to predict the rating. Now there are two ways. Customer can give the rating from 1 to 10, 10 being the highest, 1 being the lowest. Now two kind of machine learning models can be applied. One can be that multi-classification model where I can predict all the ranks, either as in 1, 2, 3, 4, 5 to 10, or I can make it that rank as a numerical ordinal value, which will it will where it will become quantifiable, and I apply an entirely different model called regression model instead of classification model. So what would happen is, the model will calculate, will try to predict the values, and the values won't be very straightforward. They won't be 1, 2, 3. They can be 1.1, 2.1, 9.1, 9.9. And then once I've got the values, I'll apply the pre-processing basing my SME only, and then recategorize the result. So we tried it both way, and the results were really amazing. So this is how the type of measurement changes what kind of technique you're going to use in data analysis. Now, another type of data is categorical. In categorical, we have categories. For example, in fund type, we have categories, right? And for this rank also we have categories, but with an order. Okay. So this was all about the type of data, the type of scales we used, and what kind of data is there, and what is statistics. So this is how it works so far. Now, coming to the validation part, the validation can be, in another terms, could be a part of exploration as well. That we commonly use this term called as EDA, exploratory data analysis. Now, to do ED on any kind of data, we always start with descriptive statistics. Statistics has two parts. One is inferential statistics, and one is descriptive statistics. Descriptive statistics is the presenting the data as is. It's a type of statistical technique which describes which describes the data as is, but from different point of representation or from different point of view. For example, I can give you a very long table with 100 column and 1000 rows. Now, what are the ways you can represent that data? Re-represent. And to say from different angle. You can make a summarize a tabular form, make a pivot, or maybe a graphical representation that will help me ingest that data better than its plain form. So that is where the descriptive stats come in. So whenever we start from exploratory data analysis, we start from descriptive statistics only. We do not jump to inferential statistics, because inferential statistics is the realm where we make calculated guesses. Now, in descriptive statistics, we have various techniques. We have graphical, tabular, numerical, etc. Now, where have you seen this descriptive statistic? I want to tell you. This descriptive statistics, the most of the statistical information in newspapers, magazines, company reports, and other publications where we have the visuals like these and some tables like these, where data are summarized and presented in a form that is easy for the reader to understand. Simply, descriptive is very simple. That it's a data in a simple another form. Now, such summaries of data, which may be tabular, graphical, or numerical, are referred to as descriptive statistics. Now, to give an example of same descriptive statistics from this data, just have a look at this, this visualization. This is called a bar chart. We, on one axis, we have the fund type and we have the percent frequency. Let's go back to the data. So in this, this bar chart is based on this entirely one column only. Now looking at this column, I know I cannot simply say, okay, which kind of fund type is the most, which is the lowest one, right? So what we did is we created a bar chart. So how to create a bar chart? It's simple. You just put what kind of unique values are there in that particular variable or column. Then you count its frequency, the number of hits that it has. So domestic equity has 16, IE has 4, fixed income has 5. Overall 25. Now what is this percent frequency? This percent frequency is nothing but this number divided by total. So what percentage share does this particular mutual fund type has in entire data? So this becomes into percent frequency 64, 16, and 20, and this is the scale we have used for this y. You can, you could have also used this scale as well. There's no hard and fast rule that you have to use percent frequency only. You can simply use frequency. Why we use percent frequency? Because it boils, it totals to a total of 100. Okay. So moving forward, the another part of statistics that I was talking about is inferential statistics. So in descriptive statistics, you saw, we have all kind of, we either create a table. This is a table, we create a visualization. And this is not just one visualization, we have multiple visualizations. We have bar chart, line chart, bar graph, box plot, pie chart, and many more BI experts are there in the call, which know which other charts, are very popular for data analysis. Now, the another part of statistics is inferential statistics. It's a type of statistical techniques which from which we can inference about a subset of data, or we can estimate about a subset of data, or we can make calculated guesses about a subset of data. And in our data analytics industry, it is also called as guess plus estimate, called as guesstimate. It's a very popular, it's an entirely different job profile that you have to guesstimate. For example, if I ask you a question that how many people travel from Rajiv Chowk metro station to Huda city center every day from 9 a.m. to 3 p.m. So that is a part of that is like one could say, okay, it's a very, one could say 10,000, one could say 30,000. Now what if I tell you there's a proper way to accurately find how many people actually travel from Rajiv Chowk to Huda city from 9 a.m. to 3 p.m. with 95% confidence. So when I say 95 and not 100, because not everything is 100% accurate in statistics. It's always lesser than 100, but higher the confidence level, higher will be the probability that this is closer to actual number. So this is where inferential statistics come into play. Now, from machine learning point of view and from BI point of view, if I say we always start from descriptive statistics, and basis that, if we think some insights from the data can be found out, or that may be hidden, or maybe a requirement of some advanced analysis, we go to inferential statistics. Now, here I have said, everything we do, we inference, we estimate, we guesstimate, or we take calculated guesses, we do on a subset of data. Now, one question should, strike your mind is, why not take superset and calculate statistics around it? Why are you, just taking a subset out of it? So the plain and simple answer that you can, give to anyone who asks you this question is, many situations require information about large group of elements. Definitely, I want to, conduct a survey. How many people will for the upcoming elections? There are around say 10,000 households in a particular ward, and how many are going with the BJP or Congress, and what other dominating party? Now, how can I say? It is actually very. It is. Maybe we don't have the time to conduct the survey to all the 10,000s. We don't have the money for that. In fact, so these are two main primary factors: time and cost, which make us go with subset and not superset. Because because of time, cost, and other considerations, data can be collected from only a small portion of the group. And when we collect data from a small portion of the group, that is where statistics comes into play. That we can infer about the larger superset from a simple subset. Now, this larger group of elements is called population, and the smaller subset is called the sample. Now, these are the formal terms used in statistics for the superset and subset. So, superset is population, and the smaller group is called sample. From sample, we calculate some parameters, we run some statistics around it, and we try to infer about the population as well. Like we have exit polls. So exit polls are not always for the full population. It is from the samples taken from different poll booths, and basis that many political experts take a call on which party is going to come, which party is going to get how many seats, and so on. So this is the real example of what you all must have seen but never thought that it's actually statistics behind. Okay. So now, as one of its major contributions, statistics uses data from a sample to make estimates and test hypotheses about the characteristics of a population through a process referred to as statistical inference. So this is the formal definition about it. Okay. Just give me a minute. Okay, so there's one more kind of data which I forgot to mention. It is called as time series data. So time series data is also a different data scale in which, when I was talking about the nominal data, the ordinal data, and the ratio and interval, there's one more kind of data called as time series data. Though it's a part of quantitative data only, but it's a different category of data as well, which you should all know about. So time series data is basically a data which changes with respect to time. For example, your height might be changing with respect to time. Your weight may be changing, and the stock prices change with respect to time. With every second, with every millisecond, they change. So this is also one kind of data, time series. Okay, let's move forward. Now, let's apply whatever we have learned so far and try to find a solution to a problem. So why I have kept this problem statement here, because this a theory is really very boring, but when you can connect that theory to real life example, it becomes meaningful and you will actually gain something from it. Now let's understand the use case, and let's see what we can make out of it. Now there's a company called Norris Electronics which manufactures high intensity light bulb which are used in variety of electrical products. Now it's a simple company which manufactures some bulbs which are used in electrical products. Now the company wants to increase the useful life of the light bulb, and the product design group developed a new light bulb filament, right? So it is more like that we have created a product and we want our marketing team to find what could be the possible customer segment for this, what could be the possible reach for this, what could be the possible sector that we can reach and sell our product. So this is what they want to find out. Now since they have got this high intensity, they have made this sorry, what they have developed, okay, they have developed a new light bulb filament, but they are not sure about it right now, that whether it will be successful or not. So what they do is, uh, they start with 200 light bulbs in starting, and they will test that light bulb and create some information, to run some statistics, collect some facts, and then they will present it to the management, maybe that, okay, on 200 light bulbs on this sample, we have got this statistics, and I think this will apply to the whole population of the light bulbs, which will be produced using this light bulb filler. So what they did is, uh, they kept the bulb on for many many hours, and they collected the data around it, hours until burnout. So burnout means the bulb got fused, the filament got burned away. For 200 sample of light bulbs. Now uh, they could have done it on 2000 as well. They could have done it on 1000 as well. They could have done it on 100 as well. Why 200? Okay. So this figure is not just right here for simple. They thought, okay, let's make 200. And why not 250? Okay. So the simple answer is, the more data we collect, we tend to say that it's a normalized data. Now, when I say normalized data, you all must have heard this term many times. Why do we need normalization? And how many number of data points will make the data normal? So this is more like it. We need let me the slide is later on in the session, but let me tell you the concept right away so that you can connect it with the real example. The more data we collect, the more generalized our statistic will become. So there are two terms, statistics and statistic. So statistic is basically the parameter, maybe the mean, the mode, the median, and what other parameters are in statistics. So the more data we collect, the more generalized our statistic or our required parameters will become, and there will be very less variation. Okay, so let's say they would have manufactured 50 bulbs and they got some answer, but can they be sure about it whether the all the population of bulb will have this kind of burnout hours only? Maybe yes, maybe not. But why 200? 200 because in stats it is stated that you should take at least 30 examples to be sure about that whether this particular statistical parameter is normalized. So this 30 has come from from 20. It's sometimes it's 25, sometimes it's 30. So you can remember both the terms. So if you have at least 30 data points for a certain element, and 30 observations, then you can state this with I would say like 60% confidence or 70% confidence that it is that all other parameters for the population are going to lie there. So it has been found out after a lot of studies by statistical researchers. So what they did is they took 200. Now sometimes what would happen is, if you take 200, if you take 500, if you take 1000, nothing is going to happen. Your final burnout average hours are going to come around the number which are close to 200 only. So minimum number is 25 to 30 and maximum sometimes goes to 272 if I remember correctly. After 272, if you want to be 95% confident, if you increase the number to 350, you'll still be 95% confident. You're just wasting your money and time, and nothing much is going to change. So that's why they took around 200 lines. So this is the hidden mystery behind it. Now we have the data for hours until burnout. Now, can anyone suggest what could be the ideal way to find how many? I mean, what should be done next so that they know certain stats about it. Now, to approach this case study, this looks very simple, and it is actually very simple, but we just have to understand the underlying approach of how statistics is applied. Now, first, we first identify the population and we collect a sample. Company wants to manufacture 2,000 bulbs. What company does it? It manufactures 200 bulbs with the new filament which were manufactured and tested. Okay, and this burnout data is collected from this sample, and this data shows the number of hours each light bulb operated before filament burnout. Now we have two things. Population will be all light bulbs that will be manufactured with the new element, and sample is the test production of 200 light bulbs. We have got the data collection. Now calculating the statistic. What they did is, they added all these 200 values all together, and then they divided it by 200 and they calculated the average burnout hours. Now, which gave them average lifetime for the light bulb 76 hours. Now, this is one way of calculating it. One could have taken the median, right? That okay, most of the data lies here. So that is how statistics proceeds. Not every value that you calculate in statistics is very accurate. Not you cannot just rely on one parameter. Okay, this is the average of it. My car gives the average of 17 kilometer in city and 20 on the highway. That is a very generalized figure, the plain simple way of calculating the statistics that we do in our everyday life. So, and this is what Norris Electronics did, because they didn't have the perfect statistician with them, which would have suggested instead of calculating the average, you should go with the median as well, and then compare the test sample. So what they did is they calculated the average lifetime for the bulb filament is 76 hours. Now, there could be case where sometimes the bulb might run 72 hours, some light bulbs might go up to 80 hours. So there's always a margin of error which is there, right? Now this margin of error actually controls the risk that you are offering while presenting this statistical figure, and it helps you understand, okay, within this particular bound range my bulb might run upon, and this is that you won't believe companies run their warranty programs. Like we have Seat tires, we have Siska LED. They say thousands hours of LED, else will take the bulb back. I don't know if they have this campaign, but if they want to run this kind of campaign, they would have tested it and they would have analyzed and got it out of the data that their bulb runs for an average lifetime of 1100 hours with a maybe a margin of error of 50 hours. So the range becomes 1050 hours to 1150 hours, let's suppose. Now if company wants to say that we now let's suppose their bulb burns out in 900 hours and everybody comes back that okay, now replace our bulb, it will be a huge cost to the company, right? So what company does is it creates a margin of error, and then basis that range, it says okay, in simple terms I would say it takes a safe bet. So what Norris did is it thought it's a 76 hours with a margin of error of 4 hours. Now, this margin of error is another statistical term, as I said. It is calculated with an entirely different method. We're not getting into method, we're just getting a flavor of it. So the average lifetime for all light bulbs would be 72 hours to 80 hours. Now this Norris Electronics could say, okay, if my bulb burns away after 65 hours. 65 hours is very less number, let's assume it is 6500 hours. If my bulb burns away after 6500 before 6500 hours, I'll replace the bulb. but that is not going to happen 95% of the time, and it can happen 5% of the time because the estimate that you have taken is 95%. Now you all must be thinking why I'm putting my uh, this why I'm pushing on 95 and not 100, because in stats we have certain figures which are called confidence interval, or you can say or you can say simply confidence. So in stats, nothing is 100%. It can be either 97, it can be 98, it could be 99.99. It won't be 100%. So the simple approach for knowledge electronic was it manufactured 200 bulbs, got the data at 76 hours per bulb, simple average, and then it used that simple average to estimate the population. So that is about it. The mean, how the statistics is applied in production industries. Now, another part of descriptive statistics, this part I think I'll take it more briefly because this is what we use in our day-to-day life and is actually very crucial to what we present to our clients. Now, in descriptive statistics, as we learned, um, we have various graphical techniques. One is bar chart, as you can see on the screen. So this figure right here is called a bar chart. It has various forms. It can be stacked or it can be grouped. This is an example of group bar chart. Stacked would be that this red would be here on top, and it would be on a normalized scale, that from 0 to 1. So it is basically a graphical device for depicting categorical data summarized in a frequency or relative frequency or percent frequency that we saw earlier, right? So bar chart is basically for categorical data. You cannot, just plot the numerical data on the bar chart. You'll have to choose a different chart. So this bar chart here, tells us which is the most popular language in development right now. So here it says Java has the most percent frequency share, or you can say the relative frequency share, or you can say the count from survey of around 500 people or maybe 100 people. So Java has the most number of share. Similarly, this is a group bar chart which is used to compare a single value within one entity. So the entity here is Washington. Maybe we are just checking how many number of males versus females are working. So this blue could be males, this red could be females, or vice versa. Similarly for New York, similarly for Chicago. And we can also compare that the males of Washington with the males of New York, and males of New York maybe with females of Chicago, and so on. Now, how do we, construct this bar chart? So as I showed earlier that you get the total unique categories in one side, you get the frequency or the count, but then you can calculate the relative frequency, which is not number divided by the total, because and this will add up to 1, and maybe you can plot this relative frequency here, maybe on x-axis, maybe on y-axis, or maybe this count here. So right here, this bar chart we can see here, it's a horizontal bar chart. Its axis have been flipped. It will not make any difference that you take this axis here or there. It's one and same information. It's only with the purposes of fitting it in the report and making it more presentable and complete. Com- yes, I forgot the word. Sorry. Okay, so though bar charts are usually used for qualitative variables, they can also portray quantitative variables, right? So right now BJP it's a qualitative variable, it's a categorical variable, but we are using it to portray the magnitude, the numerical magnitude behind it, right? So that's why I've written it here. The bar charts are usually for qualitative variables, which are the categorical or nominal, or I would say ordinal variables, but they can also portray quantitative variables. Now, we can compare, okay, TMC is going to get 12 seats, CPM is going to get 6 seats, Congress on 4, BJP on 2. Now, we can, compare these categories on a quantifiable scale. Now, another similar way of depicting the categorical data is the pie chart. It's similar to bar chart, but we have this on a pie shape form. That's it. It has same application as bar chart. And this part is called the legend. You all know about it. Now, this is about it. We all know what is pie chart, what is bar chart. Now, which one is better, right? That's the question behind it. Now, the answer behind it is if you want to compare different data sets, bar chart is always preferable. For example, this is a different data set, right? Maybe for Washington, we have different male female numbers. For New York, we have different. For Chicago, we have different. Or they may be combined in same data set only, but they are different information with respect to this entity. So that's why if you want to compare different data sets or different entities, bar chart is always preferable. Now, I cannot, just put all the information of New York, Washington here. It will be a mess like this, right? Suppose this is for New York, this is for Washington, and this is for maybe another city. Now, can I compare this fifth category of this pie chart with this category? I don't know. There's a millimeter deflection I cannot notice. So that's why if you want to compare different data sets, go with bar chart. However, if you want to part one part of data with the whole, it's better visualized in a pie chart, not in stacked bar chart, not in grouped bar chart. So no, this is a different bar chart. But let's suppose this is a group bar chart. So this visualization versus this visualization, I think this one is always preferential. So always, whenever you want to analyze part of data to whole, better visualize in the pie chart. Now, another part of descriptive statistics is tabular techniques. Now, suppose you have this data with you, that you have year which are repeating, the month which are repeating, and the categories. So it's a long tail data. It's called because all the values are repeating, and nothing from these variables could be taken as the primary key. So it's called a long tail data in data. We have types, we have sales, we have cost. Now, what could be the best way to present it? Maybe we can put some bar charts of month versus category, or maybe month versus category versus sales, or month plus category plus cost. But what if we can put it in a more tabular way that it will be more meaningful? That not always the visuals are the best way of interpreting the data. Sometimes the summarized tables are also a very good way. So it is this table is in this form. It is called a pivot, or you can say a cross table. So a cross table is a two-way table consisting of columns and rows. So we have some columns, we have some rows. In columns, we will have some categories, and in rows we'll have the recorded summarized observation. It's a multi-dimensional table. Its greatest strength is the ability to structure, summarize, and display. So what it has done is it has structured the types of fruit with respect to category and summarized it according to the year and displaying it. So this is the cross table. I know you all must have used it many a times. Now we get into more technical part of descriptive statistics, which is the histogram. Now, as I said, from nominal we added order, we got ordinal. In ordinal we added intervals, and we got histogram. So this is where we are. In bar chart we have gap, but in histogram we do not have gap because we have intervals. 0 to 5 years, 5 to 10 years, 10 to 15 years. There is no gap. So these intervals are also called as bins, and this width of the bin is called the bin width, and these are called the bin. And here we have the data of from someone's Fitbit band, that the daily steps taken by that person with respect to the count. So yeah, this is more about it. This is self-explanatory, and nothing much is there to explain in histogram. Yeah, one important aspect of histogram is that it tells you about the data distribution. So what kind of data distribution does this data follow? So you all know about this bell curve, right? This inverted bell curve, like this, it goes. Now this bell curve is also referred as the normalized data. Now again, I've come to the normalized data. Why bell curve is normalized data? We'll learn later in the session. Okay. So histogram is the graphical representation of distribution of quantitative data. We have certain frequencies on y-axis or maybe sometimes frequencies on y-axis, and it is mainly used to understand the distribution of the data that we'll talk later in the class. Now, how it is created? It's a very simple form. You just convert the data into intervals. Then you count how many categories are falling in that interval, and you plotted it on the there another axis. So let's suppose for the count from 1500 to maybe till this, maybe from 1500 to 2000, all combined we have around 22 plus 42, around 62 counts, right? So this is how it provides information on the data distribution, or which is also called as probability distribution of a continuous variable. So continuous variable is basically a quantifiable variable, which as just told about, it's a numerical value. Now, data distribution in statistics is also called as probability distribution or probability data distribution. So don't get confused with this confusion. Okay? It talks about the symmetry in data, whether data is normalized or not. So for this example, this histogram, it's decaying over period. So we call this skewed right. So this is called skewness. The data is elongated on the right side. And if the data is, decreasing and elongated on the left side, it's called left skewed data. If now this is uniform data, there's no change in data over the axis. This kind of data is called normal data, or I would say the bell curve kind of data, where the data is symmetrical. All the values which are falling from this point to this point would be identically the same. And I would say, okay, let's not complicate this part. Just understand, that histogram tells you about the symmetry of the data as well, whether data is skewed or not. Data has bimodal. Bimodal means data which has two modes in it, and whether data is symmetrical, skewed, uniform. Now, another part of descriptive statistics is the scatter plot. So scatter plot is basically a two-dimensional, figure where we plot one variable on one axis and one variable on the other axis. Like we have height and weight. Now, why scatter plot is very crucial? Scatter plot is, the end output of regression, and it is also used for many ETA applications because scatter plot sometimes is self-explanatory. How? Suppose we have plotted height and weight. Now, height is in centimeter, weight is in kgs, right? Now, basis this plotting, do we see any relationship between these two? No. What we do is we plot a trend line. Whether with increase in height, with increasing weight, is height is also increasing? Let's see. So when we are moving from 155 to 75, yes, points are coming in like that. So this is a trend line. Now one question could be, why this trend line exists and is not like this. So this is actually coming from a regression, and this is the line of best fit. So I think Manoj must have told you about what regression is and what line of best fit. So this is telling us with increase of height or maybe with increase of weight, we're getting an increase of height and vice versa. So in another terms, it's called as correlation, that these two quantities are correlated. With change in, and what correlation is, that with change in one quantity, there is change in another quantity. Now this change can be positive, that with increase, another quantity also increases, which will be termed as positive correlation. If and if it's a decrease, then it would be called as negative correlation. And sometimes one quantity increases on a very fast scale, and another attribute doesn't increase with that much fast scale. So that would be called as moderate positive correlation or mild positive correlation. So one example is height and weight. One example is income and expenditure. With increase of our income, we tend to expend more. Maybe age and blood pressure. With increase of age, we see sometimes increase in blood pressure, or some people develop low BP. So these are examples of uh, what do we say? Positive, negative, mild, moderate correlations. With and one example is advertisement and sales. So this is one crucial part of it. Suppose we have run the advertisement campaigns. Suppose you're running advertisement campaigns 10 a week, 20 a week, 30 a week, 40 a week, and you plot that data here, and you want to check whether there's more user engagement with respect to the advertisement. And you plot that user engagement data here, so you will get a clear picture. If this, if if the points which are plotted with respect to advertisement and sales are in increasing order, you can definitely what is the range where you can say strong correlation between variables. So yeah, Ankit, what range? So range, okay, I think you had asked this question with Manoj as well. Definitely, I would like to answer that. So Ankit, this range, that depends upon the kind of sector or domain where we are applying this correlation. If we, ideally we say that if it's more than zero, so the correlation lies from -1 to 1. Okay, let me just take an example in Notepad. So the correlation lies from -1 to 1, right? It's a normal scale like this. Now let's suppose here it is 1 and here it is -1 and here we have the 0. Now your question is, where do we say this correlation is? Uh, Let me read your question. What is the range where we see strong correlation between? Yeah, right. So let's suppose we have two variables, income and expenditure, and how can we say that this? Suppose one correlation lies here, right, and one correlation lies here. So can we say that this correlation is stronger than this one? Why? Because it is close to one. So whichever, so one way of calculating is to check which quantity is closer to one. Okay, whether it's -1 or it's +1. So that is one way of doing it. Closer the correlation is closer to +1 or -1, that correlation will be termed as the stronger one. Whatever correlation is close to zero, maybe this one or this one, will be termed as a weak correlation. So that is one way of saying it. Now, let's suppose, now this again depends upon whether sometimes in some industries you won't get a correlation more than zero point 0.7. So can we say that in that particular set of variables we don't have any correlation? No, that depends upon the SME. For example, with respect to credit card defaulters, right? If we have this data of let's say two variables in credit card industry, maybe say income and amount given in credit to credit card holders. Do we have any correlation in that? Yes, we do have. If you're earning higher, you will get higher limit on a credit card. If you're earning lower, you will get lower limit on a credit card. But how much correlation would be there? Would it be 80%? Would it be 0.8 or 80%? Would it be 0.7? So sometimes the thing is, you won't always get correlation like 0.8, 0.9, 0.95. Sometimes you'll get not more than 0.65, but that 0.65 will be considered as strong correlation by subject matter expertise. So with over time, when we collect the data, when we analyze the data for 5 years, 10 years, 15 years, we tend to generalize, we tend to, normalize that value and we say, okay, this value belongs to the population itself. It is no more a subset of the data, and these values, roll in the industries. So in my first company in TCS, I was in this bank itself, which was working on this credit card model itself, and they were it was very initial starting for me. So what I could make out of it today is that they were taking 0.75 as the strong correlation. This is their judgment, this is their analysis, this is their experience, this is their knowledge from the historical data. Hope that answers your question. So similarly, we have demand supply. Now, is it always true that if you plot two quantities here and this if this trend is upwards, this line is upwards, then definitely there's a correlation between them? The answer is no, because there was a very funny plot one day that with there's a rock band, Red Hot Chili Peppers, and the oil prices. So somebody plotted a diagram of the sales of this particular rock band album and the prices of the oil. So what was happening is if the sale of just a second. Yeah, hi. So yeah, what was happening was with increase in crude oil prices, their sales of album were increasing according to the scatter plot. So that is not always the case. Okay, so it's not always like for getting correlation between two variables altogether very high. The correlation is definitely there. So you have to apply second level knowledge, sometimes, and that is called as like subject matter expertise. That there's not going to be any relation between the crude oil prices and raw. Okay, so always take correlation with a pinch of salt. Nothing in statistics is 100% accurate, but that doesn't mean you don't follow it. Okay, so similarly, if the trend line is upwards, we call it positive relation between x and y. If the values are random, no trend can be analyzed from regression, we would say there is no apparent relationship. If the trend line goes forward like this, that one value is increasing and other value is decreasing. For example, when x is increasing, the y is decreasing here, right? You can say the values are plotting lower and lower. Then we say it's a negative relationship. But that negative relationship doesn't mean the cause is there. Okay, so in with correlation, we find there is a relation, but cause and effect cannot be determined. We have to do further analysis. Now, okay, let's do a simple case study so that we can relate what we have learned so far. So we have learned so far descriptive stats, the bar chart, the pie chart, the tabular graphs, and how can we utilize it for our normal data. Now, this is a case study of descriptive statistics only, where we have data of various, various beverages from Coca-Cola company, like we have Coke Classic, Diet Coke. Okay, we have Pepsi as well. Okay, we have the beverages data all around. Let's suppose this is a recorded response from 50 soft drink purchases. Now this is from the point of sale data. Let's suppose it's a very layman data here. No date is there, no customer name is there. It's just a simple attribute. What 50 customers purchased? Who purchased the soft drink? What soft drink did they purchase? Now from this, we can already make a guess. What kind of analysis we can get out of it? We can make a bar chart, we can make a pie chart, we can make a tabular form. Okay, this tabular form is nothing but uh, the data behind this bar chart and pie charts only. So from this bar chart, we can say the Coke Classic has the most number of sales, followed by Pepsi. Now here, we can have the labels, or we can just switch to pie chart simply. That Coke Classic has the highest market share in first 50 purchases, followed by Pepsi, then Diet Coke, and Sprite and Dr. Pepper are the same. Now, this is the formula for calculating the relative frequency of a class. So, relative frequency, as I told you, is nothing but the count divided by the total number. So, it is the count of that particular class, let's suppose Coke Classic, divided by the total number of. So, the total number is, I think, actually 100 here. So, that's how we're getting 38%. So the total count of that particular class divided by total number of records. That's how you get relative frequency. And when multiplied with 100, it becomes a percent frequency. It's one and the same thing. So yeah, so what we have learned so far is how to organize raw data, what are the scales of measurement, ordinal, nominal, ordinal, interval, and ratio. Always remember in this way, it will be easy. Nominal, we add an order to it, it becomes ordinal. In ordinal, we add interval to it, it becomes interval. And in interval, we take two numbers ratio, it becomes a ratio scale. Then there are two kind of data, quantifiable or numerical, or we have the qualitative or categorical. Then we have learned various techniques used in a tabular and graphical manner, which are called bar chart, pie chart, histogram, scatter plot, and there's one more plot called as time series plot. I think I haven't put the example here. So, anyways, I'll try to show it later in the class. And we also discuss the merits and demerits of each plot, like why, where it is used, and sometimes you have to take it with a pinch of salt. For example, if you want to compare different data sets, we go with the bar chart. If you want to compare single part of data with the whole, you go with the pie chart. And we have the histogram, that what merits it have. With demerits, histogram doesn't have any demerits so far. And scatter plot, that of course it tells you a relationship, but it doesn't tell you the cause and effect relationship completely. Okay, so I think what time is it? I would recommend to take a 10-minute break, because so far we have covered around 28 slides, and we are almost halfway through the session. So to ingest better, I think we should take a 10-minute break and connect back. Will that be okay with everyone? Or if anyone has any questions, they can definitely stay back, and I will be happy.
No problem. Yes, we can take.
Okay, thank you. Let's meet back at 1 p.m.